Hello everyone, my name is Pablo Medrano of FuVeX, and this is the presentation for the IEEE Census Conference 2020 of the paper UAS IoT Online Sensors for Power Line Inspections, done by José Villadangos, Javier Astrain, and myself. This work is a collaboration between the UAS operator FuVeX and the Department of Statistics, Computer Science and Mathematics, and the Institute of Smart Cities of the Public University of Navarre in Spain, Pamplona.
UAS IoT online sensors for power line inspection. Power lines are critical infrastructures in modern society as they are used to transport the energy we use on a day-to-day basis. Power lines can be found everywhere, on every kind of terrain, from populated and accessible cities and fields to dense forests or mountains, where even access by foot can be compromised. Due to their criticality, many countries enforce inspections to assure their functionality. Although some of the assessments can be done remotely, visual inspections through sensors such as thermal or optical cameras and lidars are a necessity. Some defects or problems, such as structural corrosion or vegetation dangerously close to the lines, to name a few, can only be detected visually before they actually compromise the functionality of the energy transmission system. Visual inspections can be carried out from the ground if the place is easily accessed. In a more general case, electrical companies deploy aerial vehicles for this task. Up until now, helicopters have been the vehicle of choice for inspection, as they are maneuverable, can carry a lot of weight, and can hover and get close to the power lines. Their main disadvantages are that helicopter usage is expensive, and, more importantly, that there is an actual risk of loss of human lives. Unmanned aerial systems, or UAS, have been postulated as an alternative for these tasks. The typical approach are flights in visual line of sight, which means that the pilot can always see the drone with multirotors, a type of drone with high mobility and low to moderate autonomy. While this approach reduces human risks, it implies small steps on the line while carrying all the equipment, which makes them slow and thus expensive. The third alternative is the usage of drones with beyond visual sight capabilities, which still minimizes human risks but significantly reduces expenses compared to both helicopters and VLOS flights. On the other hand, VLOS flights can rely on remote sensor operators, as the quality and timings of a possible transmission cannot be guaranteed. For inspection, and given the variability of the terrain where power lines are installed, there is also the constraint of the necessity of vertical takeoff and landing capabilities, which makes VTOLs, a mixture of multirotors and planes, the perfect candidates. VTOLs can take off, land and hover as a multirotor, but can also fly as a plane, with significantly lower power requirements for the same amount of traversed space. As a resume, the main characteristics that a VLOS inspection should comply with are usage of long-range drones with more than 10 km of reach, with hover and vertical takeoff and land modes, usage of onboard stabilization for the embedded sensor to avoid vibration and maximize the quality of the capture, usage of an inspection system capable of automatic orientation, data collection, and data processing, as direct control by a remote operator is not feasible, and usage of high-quality sensors able to capture high-quality data of the inspector. The IoT architecture is designed in a way that makes flight tasks and data acquisition tasks independent. The flight controller, the microcontroller that runs the autopilot software and controls the flight of the UAS, can transmit attitude, bearing, and position data to the Automatic Data Acquisition System, or ADAS, while the ADAS does not explicitly communicate with the flight controller. The ADAS is composed of two blocks. The first one, the computing block, is formed by a companion computer which runs both the integration software and the neural network used for detection, and by a tensor processor unit, or TPU, which accelerates detection inferences to the point of being able of processing video in real time during the flight. The integration software is responsible of combining the positional orientational data given by the flight controller and the GIMBAL block, detections from the neural network, and the a priori knowledge, and generate an order for the gimbal to point with precision to the best objective. The second block is the GIMBAL block, composed by a gimbal which houses the low-quality and high-quality cameras. The low-quality camera captures video only for processing purposes, while the high-quality camera is used to capture high-quality images for the actual task of visual power line inspection. Depending on the requirements, all the mentioned components can be relatively low power, low cost, and low weight, as our prototype shows. We implemented a system of a Marion 5 from FuVeX Civil, a VTOL powered by a Cube 2.1 flight controller running the R2 pilot firmware, and here GNSS compass module. The computing block is implemented through a Raspberry Pi 4 and a Google Coral TPU. The gimbal block is formed by a turret gimbal, a Raspberry Pi camera, a slow-quality camera, and a GoPro Hero 3 as a high-quality camera. The ADAS components, excluding the VTOL, have a combined maximum power consumption of around 17 watts, a price of around 900 euros, and a weight of less than 500 grams. Tower identification images is achieved by the use of convolutional neural network. As this is a niche field, there are, to acknowledge, no pre-existing datasets, so we had to construct one. The resulting dataset is composed by close to 41,000 bounding boxes, corresponding to two classes, power tower and tree. Of these bounding boxes, around 3,100 are from power towers, while the rest are from the tree class. The construction of the dataset was possible through the usage of the computer vision artificial tool, or CVAT. Due to the small size of the dataset, we decided for a transfer learning approach instead of a full-fledged training. The base model employed was a COCO trained SSD MobileNet V1, which was retrained for around 600 epoch for our dataset and posteriorly adapted for the TPU through quantization. Pure object identification and images discuss temporal information, which is of importance for the problem maintaining the gimbal orientated and stable. In order to use this information, we have developed a classifier based on neural networks and TULETs, temporal sequences of bounding boxes with associated scores that take advantages of this knowledge. And thus, for any given frame, there may be several active TULETs, each of them identifying a possible tower. Those active TULETs are updated depending on that single frame identifications. If a new bounding box is determined to correspond to a tubelet, that representing score and representing bounding box are updated accordingly and the tubelet keeps active. If not, a new tubelet is created from that bounding box. Tubelets that have not been matched to a bounding box for a certain number of frames of that converge, meaning that its components are equal to the ones of other tubelet, get dropped. Bounding box to tubelet match is done by IOU with a threshold. Tubelet scores depends on the maximum identification score given by the neural network to a relevant bounding box of that tubelet and the number of frames skipped by that tubelet. Its representing bounding box is a function, or we use a mean, of the coordinates of the relevant bounding boxes of that tubelet. Finally, each tubelet has a maximum number of consecutive frames up to the actual one, noted as relevant. In a scenario, we define relevant towers as the ones we wish to capture, and spurious to those we don't. Both types of towers can be identified by the neural network and incorporated into a tubelet, so additional information of which towers are relevant and which ones are not must be incorporated into the system. This is done once in global coordinated and before the flight. We also need to define the ADAS action radio as the maximum estimated distance in where, rightly orientated, the acquisition system can identify a tower in an image. In each iteration, the flight controller feeds the algorithm the position, speed, and bearing of the UAS. From this data and the knowledge about the position of the towers, we can estimate that there could be a relevant tower inside the action radio, a tower we can detect and capture. If there are not, the algorithm prepares for the most probable next tower. It creates a rectangle of certain length and width, starting from the current latitude and longitude of the UAS and following its flight direction. The next relevant tower in this case, if exists, is the closest and capture relevant one inside that polygon, and the system orientates the gimbal toward that position. If there are no relevant towers inside the action radius or the polygon, the gimbal goes back to a neutral position. If there are relevant towers inside the action radius, the gimbal should be orientated towards the closest one, and the processing of the video stream should be given inferences. Those inferences are matched against the known positions of relevant and spurious towers to discriminate between them and select the objective. The ADAS then gives the gimbal instructions to correct, if necessary, its orientation centering the image in order to maximize the quality of the capture. This process repeats until all the relevant towers are captured or the capture time end. We propose a low power, low weight, low cost autonomous data acquisition system (ADAS) for the capture of high quality visual data that operates on UAVs and in real time. Results showing the viability of the system both in tower identification and in the time needed to achieve it, derived from actual flights performed with a VTOL UAV equipped with our system. Finally, we need to acknowledge the Stardust project by UE, the Dr. PV by the Ministry of Ciencia, and Por VV Laws by Gobierno de Navarre for their involvement in the success of this project. Thank you, everyone.